Everything we see and touch has mass. But what exactly is mass? This fundamental property of matter has puzzled scientists for centuries. It determines how much an object resists changes in its motion. Mass also dictates the strength of gravity. The more massive an object, the stronger its gravitational pull. For years, physicists lacked a complete understanding of how particles acquire mass. The answer, they would discover, lies in a tiny elusive particle called the Higgs boson. The Higgs boson is often referred to as the God particle. This moniker, while catchy, doesn't fully capture its essence. Instead, it plays a crucial role in a mechanism that gives particles mass. This mechanism involves a field that permeates all of space, known as the Higgs field. The Higgs boson is the quantum excitation of this field, much like a ripple on a pond. Understanding the Higgs boson is crucial for comprehending the universe's fundamental structure. The Higgs boson is not your average particle. It's not a building block of matter like electrons or quarks. Instead, it's a force carrier, much like the photon, which carries the electromagnetic force. But the Higgs boson carries a unique force, the Higgs field. This field is what gives particles mass. Imagine a swimming pool filled with water. The water represents the Higgs field. Now imagine dropping objects of different sizes and shapes into the pool. Some objects, like a small marble, might move through the water with ease. Others, like a large beach ball, would encounter more resistance. This resistance is analogous to mass. In the world of particles, the Higgs field provides this resistance. Particles that interact strongly with the Higgs field have more mass, like the beach ball in our analogy. Particles that interact weakly with the field have less mass, like the marble. The Higgs boson itself is like a wave in this pool, a disturbance in the Higgs field. Just as a wave can transfer energy, the Higgs boson can interact with other particles, giving them mass. The more a particle interacts with the Higgs boson, the more massive it becomes. Imagine the universe as a vast, empty space, not unlike a giant container. Now fill this container with a special kind of substance, a cosmic molasses. This molasses is the Higgs field. It's not something we can see or touch, but it's there, permeating all of space. This field is what gives particles their mass. Think of it like this. When particles move through the Higgs field, they interact with it. This interaction is what gives them their mass. Some particles, like photons, particles of light, don't interact with the Higgs field at all. They pass through it effortlessly, which is why they're massless and travel at the speed of light. Other particles, like electrons and quarks, interact with the Higgs field more strongly. This interaction slows them down and gives them mass. The Higgs field is a bit like a cosmic speed bump. It doesn't stop particles completely, but it does slow them down, giving them the property we call mass. The strength of a particle's interaction with the Higgs field determines its mass. The stronger the interaction, the more massive the particle. The Higgs field plays a particularly crucial role in the universe. It gives mass to the building blocks of matter. The Higgs field, as we've learned, is responsible for giving particles mass. But how does it do this? The answer lies in a concept called spontaneous symmetry breaking. Imagine a perfectly symmetrical object, like a round ball. Now imagine cooling this ball down to extremely low temperatures. As it cools, it might suddenly and spontaneously change its shape, perhaps forming a bump on one side. This change breaks the ball's original symmetry. Something similar happened to the Higgs field shortly after the Big Bang. In the universe's earliest moments, the Higgs field was perfectly symmetrical. It had the same value everywhere in space. But as the universe cooled and expanded, the Higgs field underwent a spontaneous symmetry breaking. It settled into a new state, acquiring a non-zero value throughout space. This transition is what gave particles mass. Before the symmetry breaking, particles were massless and moving at the speed of light. Section 5. The quest for the God particle. The theoretical framework for the Higgs boson was laid out in the 1960s. Peter Higgs, along with other physicists, proposed the existence of a new particle and the Higgs field to explain how particles acquire mass. However, finding this elusive particle proved to be an enormous challenge. It required decades of research, technological advancements, and the collective efforts of thousands of scientists worldwide. The search for the Higgs boson was driven by a fundamental desire to understand the universe at its most fundamental level. It was a quest to complete our picture of particle physics, to find the missing piece of the puzzle. The standard model of particle physics predicted the existence of the Higgs boson. Finding it would validate this model and solidify our understanding of the universe's building blocks. Section 6, the Large Hadron Collider, a marvel of modern science. The Large Hadron Collider, or LHC, is not just the world's largest particle accelerator, it's one of the most complex and ambitious scientific instruments ever built. Located beneath the French-Swiss border near Geneva, Switzerland, the LHC is a testament to human ingenuity and international collaboration. This colossal machine is housed in a 27-kilometer-long circular tunnel where beams of protons are accelerated to nearly the speed of light. Powerful magnets guide these beams, steering them into head-on collisions at specific points around the ring. These collisions, while incredibly tiny, release enormous amounts of energy, recreating conditions similar to those that existed fractions of a second after the Big Bang. The energy released in these collisions can create new particles, including, scientists hope, the elusive Higgs boson. To detect the fleeting existence of these particles, the LHC is equipped with gigantic detectors, resembling enormous digital cameras, placed at these collision points. These detectors track the trajectories and energies of the particles produced in the collisions, providing scientists with a glimpse into the subatomic world. Section 7, the moment of discovery, July 4, 2012. After years of anticipation and meticulous data analysis, the moment arrived. On July 4, 2012, scientists at CERN announced the discovery of a new particle with properties consistent with the long-sought Higgs boson. This monumental discovery marked a pivotal moment in the history of particle physics. The announcement was met with excitement and jubilation from the scientific community and beyond. The data from the LHC experiments, ATLAS and CMS, provided compelling evidence for the existence of a new particle with a mass of approximately 125 gigaelectron volts. The particle's properties, including its decay modes and interactions with other particles, aligned remarkably well with the predictions of the Standard Model. This discovery confirmed the existence of the Higgs field, the mechanism by which particles acquire mass. The discovery of the Higgs boson was not just a triumph for particle physics, it had profound implications for our understanding of the universe and our place within it. By confirming the existence of the Higgs field, this discovery explained how particles acquire mass, a fundamental property of matter. This understanding is crucial for explaining the formation of stars, galaxies, and even life itself. The Higgs boson also provided further validation for the Standard Model of particle physics. This remarkably successful theory describes the fundamental particles and forces that govern the universe. The discovery of the Higgs boson solidified the Standard Model's position as our most accurate description of the universe at its most fundamental level. Moreover, the discovery opened up new avenues for research, leading physicists to explore questions beyond the Standard Model. The Standard Model of particle physics is a triumph of 20th century science. It's a theoretical framework that describes the fundamental building blocks of matter and the forces that govern their interactions. The model encompasses a diverse cast of characters: quarks, leptons, and force carriers. Quarks, for instance, are the particles that make up protons and neutrons, the building blocks of atomic nuclei. Leptons include electrons, the negatively charged particles orbiting the atom's nucleus, and their heavier cousins, muons and taus. Force carriers, as their name suggests, mediate the fundamental forces of nature. The Higgs boson, though not a force carrier in the traditional sense, plays a critical role in the Standard Model. Its discovery provided the final piece of the puzzle, explaining how particles acquire mass through their interactions with the Higgs field. The discovery of the Higgs boson, while a monumental achievement, was not the end of the story. It opened up new avenues of research and raised intriguing questions about the universe's fundamental workings. One of the most pressing questions is the nature of dark matter and dark energy. These mysterious entities, while invisible to telescopes, exert a gravitational pull on visible matter, suggesting their presence. The Higgs boson, through its potential interactions with these unseen realms, could offer clues to their nature. Further exploration of the Higgs boson's properties might also shed light on the universe's matter-antimatter asymmetry. According to the Standard Model, the Big Bang should have created equal amounts of matter and antimatter. However, the universe we observe is dominated by matter. The Higgs boson, despite its esoteric nature, has captured the public imagination, even making its way into popular culture. The term God particle, though often criticized by physicists for its sensationalized implications, has become synonymous with the Higgs boson, adding an aura of mystique to this fundamental particle. The Higgs boson has made appearances in books, movies, and even TV shows. In Dan Brown's thriller Angels and Demons, antimatter, created using the energy of the hypothetical God particle, is used as a weapon. The Higgs boson also featured in an episode of the popular sitcom The Big Bang Theory, where Sheldon Cooper, a theoretical physicist, dresses up as the Higgs boson for Halloween. The discovery of the Higgs boson marked a pivotal moment in our understanding of the universe. It filled a crucial gap in the standard model of particle physics, explaining how particles acquire mass, a fundamental property of matter. This discovery opened up new avenues of research and posed intriguing questions about the universe's fundamental workings, from the nature of dark matter and dark energy to the matter-antimatter asymmetry. The Higgs boson story is far from over. It stands as a testament to human curiosity, ingenuity, and the relentless pursuit of knowledge. As we continue to probe the Higgs boson's properties and explore its implications, we embark on a journey of discovery that promises to unveil even deeper truths about the universe and our place within its grand cosmic tapestry. The discovery of the Higgs boson has equipped us with a powerful new tool, a key to unlocking some of these secrets and illuminating the path toward a more complete understanding of the cosmos.